All right, guys, this is our review for our temperature test. Temperature test being next week. So this one's going to take some time. I think it's going to take about 45 minutes to get through this. There's about 80 questions. If you need a copy of this, then it's in the comment section below, or if you're part of my class, it's in the Blackboard. I believe in week 6 we have this as our PDF. So let's start going through it. If you download this, it'll show you like question, answer. So it'll show you the first page. Then you scroll through on your phone and it shows you the answer there. And then if you need any links like this one here, it should be a live link to bring you to the page that I grabbed the diagram from, or where I got the chart or the information that I'm using for each of the different questions there. As we go through, if you're watching this on YouTube and you have some comments, nice comments, on this review, like say I've messed something up, or I didn't understand something, or you have a better way of explaining it, then throw it into the comment section below so you can help all of us out. All right, guys, let's get started. Let's get me out of the way here. 2 seconds here. Beautiful. Okay, so let's start off with the first question. So obviously you need to be in my class, but to answer this question. But the answer here for the following temperature sensors that have been discussed in class would be B, the RTD, the thermistor, and the thermocouples. Now, if you're doing the test in my class, it'll all be available all at once. I don't like it when like each question is there, so you'll be able to see the whole test all the way through. So you can go back and keep track. Within Blackboard, it also gives you a notation of like which questions you've answered and which questions you haven't. And then you'll find that as we go through, I will say the same thing like at least 5 times. But there will be answers within the different slides and within the different questions as well. So if you're stuck, then just skip it and go to the next question, and you'll find that later on I'll probably give you the answer. A lot of the answers are within the diagrams as well, so take a look at the diagram that corresponds to the question. So number 1 is B, guys, RTD, thermistors, and thermocouples. Number 2, a positive temperature coefficient, PTC, means that as the ambient temperature increases, the resulting resistance of the temperature sensor. So I got to leave you some time to take a look, answer it, and then we'll move on. So there'll be a little bit of a pause as I say each of the questions here. But we can see here a positive temperature coefficient. So the first letter tells us exactly what's going on with this guy, right? So P is a positive temperature coefficient, means that as the ambient temperature increases, the resulting resistance of the temperature sensor increases as well. So be careful with this. This graph has both things. This is the PTC graph right there. Okay, so this one is for our PTC, that as the temperature is increasing, then the resistance is exponentially increasing as well. Okay, so PTC, we're going to go through the difference between PTC and NTC as we go through. Amatherm has a great description right here at this live link if you want to pause and go and take a look at this. Number 3, a negative temperature coefficient. Okay, so the first letter is telling us exactly what's going on. It's a negative temperature coefficient. Means that as the ambient temperature increases, the resulting resistance of the temperature sensor is going to do the opposite. It's going to decrease. So here we can see that our temperature is increasing, but the resistance on this side is decreasing at an exponential rate there. Okay, so then there's different uses for NTC versus PTC. NTC are used for temperature sensors, whereas PTC are used as a solid state current limiting device. Okay, we'll see here that 10 kiloohms at 25 ohms will be the answer to a subsequent question. Number 4, which of the following is the cheapest temperature sensor? Still accurate, but costs the least. So out of the 3 diagrams, you can see that this guy right here looks like the simplest design, and that one is a thermistor. So this might be pretty good to have in front of you during the test, having one of these charts here where it tells you all the characteristics of the 3 temperature sensors that we've talked about so far. Okay, so the cheapest here, so it says medium, but they're dirt cheap, right? Piece of metal oxide with 2 leads on it. Number 5, which of the following exhibits the slowest response to changes in ambient temperature? So for this one, it's an RTD. Again, having this chart out will help you during the test, right? So the RTD, we can see for the sensitivity there is the slowest. Okay, so the slowest response to ambient temperature changes would be the resistance temperature detector, or RTD. Number 6, which of the following temperature sensors is the best choice for environments where this sensor will have to withstand the heat of an open flame? Okay, so for this guy, the one that corresponds to the open flame would be the thermocouple. Right? We can see here for the thermocouple that it's good up to at least 1800 degrees Celsius. So this would be our best bet for an open flame. Right? Thermistor will definitely smoke. RTD would probably be able to handle open flame, but a thermocouple would handle it for longer time. Number 7, which of the following temperature sensors has the fastest response time? So out of these guys, the one with the quickest response time is actually the thermistor. Whoa, that's fuzzy. So for this one, it's the dirt cheap one, but it's also quick and fast acting. Number 8, which of the following temperature sensors exhibits self-heating? So self-heating is the fact that you have a temperature sensor that's basically like a variable resistor, in that the resistance changes with changes in temperature. But as you have current flowing through that portion of the circuit, then it's going to heat up the actual temperature sensor and change the resistance. So out of these guys, the ones that exhibit self-heating would be the RTD and the thermistor. This one I find is the best chart out there from National Instruments. So have this one out during the test, and it'll give you a lot of the answers as we go through. We can see here that both the RTD and the thermistor both have self-heating. Okay, self-heating being that current is flowing through the sensing element, and as current flows through it, it heats it up, which changes the resistance slightly. Number 9, which of the following temperature sensors is considered to be the most expensive? So out of these guys, especially now with prices going up, the most expensive would be the RTD. The RTD is the most expensive because it's made of platinum wire. But it's also like in the makeup of it as well, and that RTD takes a little bit more to actually create than the other two. So RTD is your most expensive. Number 10, which of the following temperature sensors is the most susceptible to electrical noise? So electrical noise would be magnetic fields, signals from our cell phones, radio waves, and essentially the ones out of these three that are like an antenna would be the thermocouple. So the thermocouple is basically just two straight wires that as these waveforms pass or magnetic fields cut across, then they're like a big ass antenna. They're going to pick up all kinds of noise. And then it creates a millivolt output as these waveforms cut across the conductor that are going to induce a voltage as well, which is going to screw up the millivolt output that we get at the open end there. So the ones that act as an antenna are the ones with straight wires, which are essentially the thermocouple. Number 11, which of the following accurately describes what a thermistor is? So as we go through here, we'll see like process of elimination. I'll ask you about the three different types of temperature sensors that we talked about so far. But as we go through, you can eliminate one by one and be down to like a 50-50 chance. So a thermistor is a solid state device made from a highly sensitive metal oxide. Number 12, which of the following accurately describes what an RTD is? Okay, so we said that it's not this guy, right? Because we just answered that for the thermistor. So now we got three choices, and we've said numerous times, or I've said numerous times, that an RTD is made of platinum wire. So 12 is a coil of platinum wire wound around a ceramic core. Okay, two different forms etched onto the ceramic substrate or wound around the ceramic core there. Now we've answered two of them, so now we should be down to a 50-50 chance, right? We can eliminate D, we've already answered that. Coil of platinum wire was already used as well. And so which one accurately describes what a thermocouple is? Thermocouple is two dissimilar metals joined at one end, right? But we have, in this case, we've got it down to a 50-50 choice. So 13 is B, two dissimilar metals joined at one end. Number 14. So I want you to be able to recognize different temperature sensors out in the field as well. So these diagrams, or this diagram right here, some of them look like this guy looks like a Zener diode. This guy looks almost like a capacitor, but all of them are thermistors. So the telltale one would be something like this, right? For a thermistor found on your thermostat or your phone, right? So 2 leads, variable resistor, but out of all of them, that's the thermistor would be the one that would be on your phone or on your thermostat at home. Number 15, which type of temperature sensor is shown below? Okay, so for this one, there's a number of things. So right here, we see that we have a yellow and a red lead. So that tells us which temperature sensor it is. Then we also have these specific connectors here as well. And we can see that there is a polarity on this guy. And we can see that one is thin and one is thick. So for all of these guys, all those clues, they tell us that it is a thermocouple. Thermocouple has 2 dissimilar metals, and then in this case it has a red and a yellow lead coming out of there, right? Remember that it creates a millivolt output, and that it creates a millivolt polarity output. So 15 is B, guys. Number 16, which type of temperature sensor is shown below? Okay, the process of elimination. We've already talked about the thermistor, the thermocouple. This one is the RTD. How would we know it's an RTD if this was the first question? Well, the fact that it has 3 leads. So 3 leads would definitely tell us that it is an RTD. Right here we have 2 reds and 1 white. Number 17, which type of temperature sensor is shown below in the following applications? So here we've got a smoke detector, meat thermometer, and in line with the battery bank. So all of those guys would be a thermistor. Okay, yes, there is a thermistor in the fire alarm. Remember that you can't just put an open flame to one of these heat detectors, and that's because as a thermistor, thermistor is only good for 200 degrees. And embedded in the meat thermometer is the thermistor on the end there. And then in line with the battery bank, this one would be more used for like current limiting, and if it's in series with your battery bank there, right? Or could be keeping track of the temperature of it as well. Number 18, which type of temperature sensor is normally found in every household appliance? So in your house, the temperature sensor that's going to be used the most is going to be the thermistor. It's in the coffee machine. It's in the fridge, the stove, the microwave. It's in every one of those guys. The beauty of that is we now know that we can take the thermistor and test it with the ohmmeter to see whether it's good or not. We don't have to phone the appliance guy. Number 19, which type of temperature sensor is shown in these applications? Well, these guys are all high heat, right? Glass and steel. So anything with high heat is going to be the thermocouple. Number 20, which one is the temperature sensor being depicted below? So remember that for a thermistor, the PTC looks like this, and the NTC looks like this. So that's how I remember this one. This kind of looks like an exponential curve there. So it's a rectangle with an exponential curve hockey stick that's there. Each of those guys are there for the thermistor, a variable resistor that exponentially changes with temperature. 21, okay, this one looks like a thermocouple, right? And it has the 2 polarities that are there. We know that on this guy, and just bear with me. I say the same thing like 10 times just to kind of hammer it in over the 45 minutes that you're watching the video here. I'm hoping that by the time you're done this video, there's very little studying that needs to be done, because when you go to sleep, you'll hear free in your head going over all these different questions and terms. So 21, this one here is the thermocouple. Again, process of elimination, we know that the next one is the RTD. And this one is a resistor with a line through it. And the line through it, this arrow here, denotes that it is a variable resistor. 23, which of the following temperature sensors produces a large change in the resistance with temperature changes, but is very non-linear? So we just showed on the previous slide that the thermistor is the one with the exponential curve. 24, a thermistor's resistance or output voltage changes when the temperature to which it exposes varies. So I would stay away from this as a teacher for a test question because both are correct. Ultimately, the best answer is resistance, right? Like when we created this voltage divider circuit and had the thermistor, the variable resistor, we were looking at the voltage between 1 point and ground, right? So we looked at the voltage across this guy right here. But as the thermistor resistance changes, the voltage across it changes as well. So best answer would be resistance, but you know it's also with the resistance change a voltage change as well. So I will try to stay away from the watch. I'll probably use this on the test by mistake, but I try to stay away from questions like this, like where it says best answer. Best answer is awful as a teacher to use. Okay, so 24 is resistance. 25, NTC thermistors resistance decreases as the temperature. So we can see here that the temperature is increasing as the resistance decreases here. So the answer here is increases. Okay, be careful with the next one. It says PTC thermistor resistance increases. So here we can see that the resistance is increasing, but it's also as the temperature increases as well. So 26 is increasing as well. But be careful where we have something like this. 25 increases, 26 increases. Your brain's going to try to trick you because the previous answer was increase. So then you're like, oh, this has got to be decrease, but they're identical. So be careful on questions where they have the same answers side by side. I'm losing my voice here. Okay, also be careful in trying to change your answer. Your initial answer was correct. You're not giving your brain enough credit, right? Your brain has already done the computations, found the answer, and spat it out for you. If you go back and change that, you're wrong. It was your initial answer that was correct. You have to be super clear on the fact that when you change that answer, that you've gone through exactly why you want to change that answer. It's most likely that the initial answer was correct. And be careful with the placement of questions side by each here, in that it's going to trick you psychologically as well. 27, how many leads does a thermistor have? Well, I'm going to give you a diagram of the thermistor, and I can only see 2 leads on these bad boys. So 2 is the answer there. Okay, every question should have a diagram that corresponds to it. 28, because during the test is supposed to be learning as well, right? It's not beating up and everything. It's just reinforcing and learning throughout the test. Hopefully at the end of the test, you're like, that was it was good. It covered everything that we covered in class. It was fair, and I actually felt like I learned something during the test. 28, NTC thermistors have the first letter is telling us the relationship. So that would be a negative temperature coefficient. Take a look at this one. So be careful with these questions because they're a little counterintuitive. If the temperature in the figure below increases, current in the circuit will. Okay, so this one is an NTC, right? So an NTC means that as the temperature increases, and is that what's being asked? Yes, temperature is increasing, right? Okay, and we want to know about the current. Okay, so we want to know about the current in the circuit there. So, but temperature is increasing. This one is a negative temperature coefficient, so that means that the resistance is going to decrease. And as the resistance decreases, then the current is going to increase in the circuit there. Okay, let's see if I'm correct. Yes, increase. Okay, so temperature goes up, resistance goes down on the thermistor. That's the only thing in this circuit right now. And so the overall current in the circuit will increase. So 29 is A. 30, a simple technique for converting the variable resistance of the thermistor to a voltage. So again, it gives you the answer to your previous question, is to use a circuit called, so this was what we did in week 1 and week 2. We created a voltage divider first between 2 resistors, and then between a resistor and the variable resistor of the thermistor. That's a lot to say. But the term for 2 resistors in series, where you look at the voltage between the center tap and ground, is called the voltage divider. Just sets up a ratio. 31, if the temperature to which the circuit in the figure below is increased, okay, so we're just making a note saying temperature is increased, and we're looking for the voltage measured by the meter. So this is what we're looking for right here, okay? So temperature is increasing. This is an NTC, so the temperature goes up, which means that the resistance goes, the resistance goes down, and the voltage across this guy is dependent or proportional to the resistance. So if the resistance goes down, then the voltage on the thermistor here is going to go down as well. But that's not what they're asking. They're asking about the voltage across this stationary resistor right here. Now, we know that Kirchhoff's law is that Vt is equal to V1 plus V2, right? So Vt, I'm just going to arbitrarily make this V1 and this V2, right? So we have seen that V1 voltage is going down. Well, they both have to sum to give us the Vt, so that means that V2 is going to go up. So the answer here is that the voltage is going to increase with an increase in temperature there. So answer is increase. So hopefully you can see through my chicken scratch there how I figured that out there. I first found the voltage across the thermistor, and then that told me what was happening in terms of the total voltage, how much of that voltage across the stationary resistor was increasing. So 31 is A. 32, thermistors are accurate to approximately how much? So they were dirt cheap, super fast, and deadly accurate. So 0.05 degrees Celsius to 1.5 degrees Celsius as well. 33, the working temperature range for most thermistors. So remember that if we put an open flame to this, schmuck in a pancake, so 0 to 200 degrees. Some are in your oven, so some can go above that, but the general range for a thermistor would be 0 to 200 degrees Celsius. 34, a 10 k ohm thermistor will exhibit this nominal resistance typically at which temperature? Well, the answer is right here on the chart, right? So we can see here that it's at 25 degrees Celsius. That's where it's giving us the 10 kiloohms of resistance. So this is why you can test out all the thermistors in your home without having to phone the appliance guy. You take it out of the circuit, and without any current applied to it, then it should just have a resistance. Right now in the middle of winter, your house is probably around 20 to 22 degrees. So you're going to see around 10,000 ohms on that unit. But answer here for 34 is 25 degrees Celsius, given to us right here in the chart. 35, well, now this is a big word salad. So big word salad is going to mean that it's most likely going to be true, but let's see. While the primary use of thermistors are as resistive temperature sensors, being resistive devices belonging to the resistor families, PTC thermistors can also be used in series with a component or device to control the current flowing through them. In other words, they can be used as a current limiting device. That's true. So this one right here is being shown in a drive, but they're also in series with light fixtures and with smaller motors as well. So remember that as the temperature goes up, then the resistance on these guys exponentially increases, and as resistance goes up, current goes down. So they're a way that they can reduce the current on their own as the current increases. 36. I got a tickle in the back of my throat. 36. When a higher current is applied to a load in series with a PTC, the resultant resistance of the PTC thermistor is, well, if the current is going up, then the temperature in the circuit is going to go up, and the resultant resistance is going to be high, right? So here we can see that as the temperature goes up and it's a PTC, the resistance is going to exponentially increase as shown right here. Excuse me. 37. Change in resistance versus ambient temperature for thermistors is a non-linear exponential curve. So that gives us the answer to previous questions. Therefore, in order to obtain an accurate signal that corresponds to the temperature of the thermistor, which equation is being used? So the only ones that aren't criminals there would be the Steinhart-Hart equation. Okay, so these guys were guys who had, they were doing research on the temperature of the oceans prior to, you know, the understanding of global warming. And so they had a thermistor as the temperature sensor. Weren't getting the best output of that guy or best results, and so they just created their own equation. So there's the Steinhart-Hart equation. That is a logarithmic equation, which I believe will be shown on the next slide. There we go. For the Steinhart-Hart equation, so that gives you the answer to this guy. The resultant temperature of this equation is in which temperature units? So this one, with the Steinhart-Hart equation with the coefficients A, B, and C, will provide us with an output in Kelvin. Okay, remember that in our Arduino code, we had two lines of code, one to change it to Celsius, one to change it to Fahrenheit. But the output of this equation right here is in Kelvin. 39, an RTD. We've mentioned this numerous times, but an RTD is a precision resistance whose resistance changes with temperature changes. Number 40, RTDs have the following characteristic change in resistance versus ambient temperature change. Okay, so they're the same as RTD is made of platinum wire, but it's the same as aluminum wire or copper wire. As you heat that up, then the resistance is going to increase. RTDs, they try to use an RTD where it provides us with a linear output there. So this one will provide us with a positive temperature coefficient that is fairly linear in scale. So 40 is A. Halfway there, guys. I don't know if my voice is going to last, but we're halfway there. 41. I recorded this whole thing earlier with my microphone not working on my software. So that's why I don't have a voice. 41. A PT100 RTD has a resistance of 100 ohms at an ambient temperature. So this one is at 0 degrees Celsius. So we can see here in the chart for the PT100 that at 0 degrees Celsius, that's where we're getting the 100 ohms. Okay, we saw two different types of RTDs in lab, PT100 and PT1000s. If this was a 1000 that is 0 degrees Celsius, it would be giving us 1000 ohms. So 0 degrees Celsius is the reference temperature for RTDs. 42, the most common metal used for RTDs. So we mentioned this numerous times now. So you should have this one is B, platinum. 43, and so you can see that we're rocking through these questions now. I'm giving you 80 questions. I believe in the test I give you 60 or 65. But there should be ample time to get through each of these questions here in the hour that is allotted. Which one has a positive temperature coefficient? Okay, so it's not the NTC, right? So we can eliminate A because that's a negative temperature coefficient. The thermocouple gives out a voltage output, and a thermopile we'll see is a number of thermocouples in series. So the only one out of those guys that is positive temperature coefficient is the RTD, right? It's hard to see here, right here, but they basically try to grab a portion of that curve that is fairly linear for the RTD. 44, from the following PT100 resistance temperature chart, what's the expected resistance measurement from a PT100 RTD at an ambient temperature of 100 degrees? Okay, so the way this chart is set out is that this is 100, this is 101, this is 102, this is 103. And so here we have 100, and it looks like our at an ambient temperature of 100 degrees, we're going to have 138.51 as the answer. So the answer should be C. Excellent. Guaranteed, I'm going to give you a question where I give you a temperature and you have to find me the value on the chart. 45, which configuration is the most commonly found RTD in industry? So we found that there's 2 wires, there's 3 wire, and 4 wire combinations. 2 wire is the least accurate, 3 wire gets a little bit more accurate, 4 wire is deadly accurate but only used in labs. So 3 wire is the one you're going to see the most out in the field. So the color code does not refer to what I have here, but the 3 wire that we were using had 1 white and 2 red leads. 46, the working temperature for most RTDs. So it's going to be larger than the thermistor, but less than the thermocouple. So it's minus 200 to 850. Now I grabbed this from this chart right here, But again, different web pages and different textbooks will have different, and different manufacturers will have different ranges there. But essentially it's like, you know, minus 200 to, you know, around probably maximum 1,000, but not even there. We put a flame to our RTD in class, so it definitely can handle some high heat, but not like in the thousands of degrees. 47, a PT100 has a characteristic change in resistance due to changes in the ambient temperature. This is called the alpha value. Typically for a PT100 RTD, for every 1 degree change in temperature, the resistance is going to increase. Well, let's see. Looks like for every degree change, it's going up by 0.39 and another 0.39. So they must be rounding there. And the answer there must be B, 0.385 for each degree Celsius that it increases. 48, most common RTD. So out of these guys, the ones that we saw in lab were the PT100 or the PT1000. So 50-50 choice. Most common is the PT100, giving us 100 ohms at 0 degrees Celsius. And again, there's the answer to a previous question. 49, the issue with 2-hour RTDs. So there's two answers that I would choose. So RTDs give you a linear, so we can eliminate this guy. Cold junction compensation is not needed for RTDs. So now we're down to a 50-50 choice. This is one of those best answer ones. So an RTD does exhibit self-heating, but the best answer there would be the issue being the resistance of the lead wires. So the wires that are connected to the RTD are going to distort the total resistance being shown in the circuit there, especially with the 2-wire RTD. So best answer there is the resistance of the lead wires distorts the accuracy of the sensing element of the RTD. 50, what's the expected resistance reading between the two red leads? So between these two guys, which are joined together, that must be a really low resistance, right? Because they're essentially the same piece of wire. All we're seeing is the resistance of the conductor there. So between the two red leads, we're going to see like 0.6 to 1 ohm, basically a short circuit. What's the expected resistance reading between any of the red leads and the white lead? So that is the resistance between these guys or between these guys. And at a temperature of 24 degrees Celsius, our expected resistance value is going to be 109 ohms. So again, between these guys, we're going to see 109 ohms of resistance at 24 degrees Celsius. 52. Thermocouples consist of a pair of wires made of dissimilar metals joined together one or more junctions that generates a voltage when subjected to a temperature gradient. This phenomenon is known as, so we can get rid of stuff, right? Get rid of the Seinfeld effect. Seinfeld effect. It's not a full photovoltaic, nothing to do with sunlight. And piezoelectric effect is something where we have a sound wave going across a crystal. So the answer there is the Seebeck effect. So Seebeck was the gentleman who found that as you heat up one end and have the whole circuit closed, you'll have milliamps of current that are flowing. And if you open it up, you're going to generate a millivolt voltage at the output there. Nothing that can actually, turn on a relay or a contact there, be hard pressed to turn on an LED. You have a very, very small, disgustingly small voltage that gets developed there. That is the Seebeck effect. 53, if we were to open one end of the Seebeck circuit, so if it's open, there's no current flowing, right? So that means that current answers can be eliminated. Now we have a 50-50 choice between these guys. If we were to open the one end of the Seebeck circuit and apply heat at the closed end, a voltage will develop between the two junctions. A voltage will develop between the two junctions. That's the same. In proportion to the temperature difference or in proportion to the difference in resistance. So the answer would be due to the temperature gradient there. So 53, best answer is C. Sorry guys, 54, a thermocouple consists, we've talked about this, two wires of dissimilar metals. 55, a thermocouple produces a voltage that is proportional to, so it's actually proportional to the difference in temperature between both the hot and the cold junction. Let me see if I have a question there. No, I don't. So let me just do a diagram there. So the thermocouple, when you read the millivolts output at these two open ends here, it's because of, here we have the hot junction, right here, where we're going to have a millivolt developed as we heat it up. But at the cold junction, we have ambient temperature that's also going to create a millivolt voltage. Those two guys are going to be countering each other. And the voltage that we're actually going to see at the open ends is going to be the difference between the hot junction and the cold junction between those two voltages. So 55, the answer is A. The output voltage is based on the difference between the hot junction millivolt output and the cold junction millivolt output. 56, when using a multimeter instead of a calibrator connected to the thermocouple to obtain the temperature of a liquid, the ambient temperature of the terminals must be corrected by adding the millivolt that corresponds to the ambient temperature to the millivolt indicated on the meter. This is known as the cold junction compensation. So this is from a calibrator. So you can see that the thermistor is in line there, and the thermistor is there with this heat-sensitive paste on this larger heat sink here to keep track of the temperature and negate the temperature at the cold junction. So the points at which we actually read the millivolts would be these 2 points right here, and we need to know what the temperature is there. So that's where we're using the thermistor to determine that temperature and negate the voltage that gets developed there. It's called cold junction compensation. 57, the name for the end of the thermocouple where the two dissimilar metals are joined. So that is this point right here. That's the hot junction. Okay. And then the cold junction is where you're actually reading the millivolt output. It's a hot junction because 99% of the time we're putting a flame to this end. This end could be colder than this end, as we saw with the ice bath experiment, but most of the time you're heating up a thermocouple. And so the cold junction will be at the ambient air temperature. 58, type J thermocouples are constructed using these two types of dissimilar metals. So type J would be these guys right here, and it looks like it's iron and constantine. Now this also gives us an answer to subsequent questions with the color code for the type J, but we'll get there in a few seconds. 59, the other type of thermocouple that we looked at was the type K, and type K looks like it's made of chromal and aluminum. So different metal combinations there for chromal and aluminum. Again, color code is denoted right here. 60, what's the color code and polarity for a type J thermocouple? So that was on that chart that we just looked at. So type J looks like the color code is going to be white and red. Okay, I'm going to ask you a question on the red conductor, but just keep track of this guy and the next question, and that'll give us the third question in a couple of seconds there. So white and red is the color of a type J. Then I'm going to ask you a question on the color code for type K. And the color code for type K is yellow and red. Okay, again, look at the polarity of the red conductor there, and that'll help us out with the next question. So 62, based on two previous answers, what polarity is the red conductor of a thermocouple in North America? We can see that it is always going to be the negative there. So here we can see the red conductor is always going to be the negative polarity output there. Most likely you're going to see either a J or type K thermocouple out in the field. 63, you're almost there, guys. When the reference junction is at the same temperature as the measured junction in a thermocouple circuit, the output voltage measured by the sensing instrument will indicate, now this may have screwed you up in lab. So the example I'm going to give you here is we had the hot junction in room temperature water. The cold junction was at room temperature. Easy now. So the two temperatures are the same. This is going to create a millivolt. This is going to create a millivolt output, but the two of them are going to counter each other. So now we have two of the exact same voltages being developed within the same circuit. And if we looked at the voltage between the two open ends, we would see no voltage as an output there. So it's counterintuitive. But the voltage you see on the open end is the difference between the hot junction and the cold junction. In this case, they're both the same, so they cancel each other out, and we see no voltage output whatsoever. '64, in thermocouple circuits, cold junction compensation is used to eliminate error due to, so it's all due to the varying ambient temperature. So here we have the thermocouple, right, closed end going into the meter, but we have to put in a thermistor there to keep track of the ambient temperature at the cold junction, and that way we can eliminate the millivolt output that's being developed right here, because we can't discern what the millivolt output is, right? We can't, if we go back to this guy right here, we can't discern one voltage from the other on the meter. So we need something else to tell us what the temperature is, and then from the chart, that would tell us the corresponding millivolt output based on ambient temperature on that heatsink. 65, an arrangement of several thermocouples wired in series for the purpose of increasing sensitivity is called a thermopile. So you'll see this, like if you have a propane fridge or something at your hunting camp, there is no battery there. And so what it is a number of different thermocouples that are all wired in series that create in series a decent amount of voltage that can actually be used to open and close the gas valve. So you'll see that heat from the flame creates a large enough voltage to open up the gas valve, so you can have a propane fridge that doesn't need to have a battery backup system. 66. The something junction of the thermocouple is considered to be the reference junction. So the reference junction is going to be the cold junction. So where the meter is actually looking at the voltage, right? So looking right here, cold junction and reference junction are the same. 67. Thermocouple is basically, we've mentioned this numerous times, two dissimilar metals join at one end and open at the other end. Okay, be careful with the wording here. These guys are almost exactly the same. 68. An increased thermocouple output voltage can be obtained by wiring two or more thermocouples in parallel. So remember that in parallel, voltage remains the same, so this answer would be false. If you wanted to sum the output voltages of the thermocouple, you would do it like we saw in the thermopile, where the thermocouples are all wired in series. 69. The higher the temperature of heat applied to the closed end of a thermocouple. So remember that a thermocouple is an open circuit, and so we're going to have a voltage develop, and the higher the temperature, the higher the voltage. So they're directly proportional. So 69 is C. Okay, it all says open leads, so no current can flow in an open circuit. A voltage or pressure can be developed, but no current will flow. 70, which of the following is not a temperature scale? So we mentioned Celsius, Kelvin, and we haven't mentioned Rankine yet. I don't know if I pronounce this Rankine or Rankine or Rankine, not sure. I'm going to call it Rankine. But the one that's not a temperature scale is the Seebeck effect. So this would be another chart to have open during the test, giving you all the different Celsius, Fahrenheit, Kelvin, and Rankine values at absolute zero, freezing point, room temperature, human body, and boiling water in a Finnish sauna. 71, the something temperature scale has the same slope as the Celsius. So which one is related to Celsius? But it has been modified to have the lowest value at absolute zero equal to zero. So the one that corresponds to the Celsius scale would be the Kelvin. Okay, 72, the temperature scale that has the same slope or is related to the Fahrenheit scale but has been modified to have the lowest value, absolute zero, equal to 0. So the one that's corresponding to Fahrenheit is the Rankine scale. This one right here. 73, what's the correct Fahrenheit to Celsius conversion equation? Looks like it's Fahrenheit minus 32. Looks like divided by 1.8. So that's our answer right there. 73 is D. 74, what's the correct Celsius to Fahrenheit conversion equation? So that would be B. Okay, 75, absolute zero on the Kelvin scale. So that's right here. Absolute zero looks like it's equal to 0 Kelvin. 76, absolute zero on the Celsius scale. Celsius looks like it's going to be a balmy minus 273 degrees Celsius. So I believe absolute zero is where like there's no cellular activity whatsoever. 77, almost done, guys. What's the equivalent Rankine temperature for absolute zero? So absolute zero looks like it's going to be 0 Rankine as well. That's the reference temperature, absolute zero for both Rankine and for Kelvin. 78, absolute zero on the Kelvin scale. Absolute zero on the Kelvin scale is equal to 0 Kelvin. I swear I think I just asked you that question. 79, absolute zero on the Fahrenheit scale. Looks like it is a breezy minus 459 degrees Fahrenheit. And last question, conversion here. What's the equivalent Fahrenheit temperature for a value of 100 degrees Celsius? That is 212 degrees Fahrenheit. Excellent. That's all I got, guys. Let me just bring myself back up. All right, so that's everything we got. Hopefully you won't have to study very much for the test. We've already gone through 80 questions here. You already have 6 weeks that we've gone through all 3 different types of temperature sensors and wired them up to our Arduino. And we've looked at the physical characteristics of all 3 throughout the past 6 weeks. So hopefully by watching this video, you'll just maybe look at it briefly before the test, and then you should be good to go. All right, guys, thanks very much for your patience. We'll see you soon.